everyone get that homework? There's some complicated instructions to go with it, so everyone with me on what we'd like you to do for homework tonight. It says it on your sheet, so. Okay. All right, well, we've got one more set of thoughts about finding the volume of stuff today. And so we'll be talking about something called the shell method today. Notice where we are. We've talked about potato chips and lifesavers so far. That's been good. So today we'll talk about one of these other pictures. Yeah.
The homework on the board is different from what's on the paper.
Is it?
Do we do 25 through 37? Like, do we do 25?
Oh, I'm sorry, 35 through 37. It should say the same thing as what's on there. Yeah.
I was just suggesting.
34 through 38.
Yeah.
You're doing all of those. You're also doing 35 through 37 without a calculator. Of those, so that's, I guess we should have said just, I don't know, I guess 34 is the only one that needs a calculator. And 38, I guess. I don't know how we want to say that best. And then 30B and 31B with this new method. Also do them, even though the instructions say to do it one way, also do them with this new method today too. Okay. So we'll start by, let me actually have, no, I don't think I have this one on there. So you'll copy this one down. So I think you can quickly visualize this. So put this in your notes. X equals 2, y equals 0, and x squared plus 1. So we've got x squared plus 1. We've got y equals 0, and x squared plus 1. We're rotating this time around the y-axis. So I'll just review with you. Hopefully you've already started to visualize what this looks like. But we get this kind of region. You know, it's this here. It's x equals 2, the vertical line. We should also say the y-axis, I guess. Oh, no, it also, all four of these things, right? The y-axis and y equals 0. So the y-axis, the x-axis, x equals 2. So this region bounded by these four boundaries here. And we're going around the y-axis. So I think already you have, from yesterday, this should make sense. There is one small snag. Can someone just highlight what the snag is in terms of like thinking about yesterday? How would we resolve this? It's not a huge snag, but it's a little snag. Start setting it up and you'll see it maybe. How would you actually set this up? We're going around the y-axis. What do you see?
2 minus from 1 down 0.
2 minus.
That's what we would do the top left.
Yeah, so I mean, so down here, I guess the from 1 down is the issue that you're highlighting. Yeah, what is happening from 1 down here? It's still a doable problem here, and that still produces a solid for us at this stage here. Just what is that bottom part?
It's just a cylinder.
Yeah, so we got to kind of maybe, the approach, if we're doing this in a fashion like yesterday, we've got to approach this kind of in 2 sections here. We'll divide this region into 2 parts. If we're up above this dotted line, y equals 1, then we'll proceed as normal. Maybe we'll integrate from 1 to 5, looks like. And we'll do outside radius times inside squared minus inside radius squared. But then at the bottom, we'll just like have a cylinder is what that's. So you can use integration, or you can just calculate using your volume formula for a cylinder. So we'll highlight this way, and then I've got a second way that we'll do it too. So there shouldn't be any huge surprises on this one, except for what we just talked about. There shouldn't be any major surprises here. So big R is, of course, what? For this problem, what's the outside radius? We're going around the y-axis. 2, always 2, regardless of what y value you're at. The outside radius is 2. And what about the inside radius in blue? That takes a little more work to think about. Root something? Yeah, root y minus 1, right? Keep in mind, just like we just did even on the last part of the warm-up today, we need that in terms of y. Everything here, if we're cutting horizontally here, and we're going around the y-axis, everything here needs to be in terms of y. So we got the functions in terms of y. We've got the limits of integration for this guy, 1 and 5 in terms of y. And dy will be our width of our strips. So this is just like yesterday. And then this over here is what? What's going on there? Well, interpret the whole thing. Make sure you like everything I wrote down. Take a second to digest it, and then I'll like show you the rest of the work. You like everything I've written there? Make sure you can say where every number and symbol comes from. Yeah? And actually this one's not too bad to do by hand. Root y minus 1 squared is y minus 1. So we have 4 minus y plus 1, so it'd be just 5 minus y as the integrand. And we've got a 4 pi for the volume of the cylinder. Integrating here gives us this, and you can check my work if you like, but again, the emphasis is not that work. The answer we get is 12 pi. So I'll give you a second to digest what we've said and make sure you're feeling good about it, but then I'm going to go through and do it. We're going to do it a second way, using a new technique that I think you're going to like. While you're digesting that, I'll start these things happening. We got this. Why do we have this? Huh? Because we studied yesterday and just now. Even what are these? They're washers, right? They're washers. Okay, you can imagine cutting some of the things we've been looking at into a shape that has all these constituent parts. So you just have to go around and relive your childhood. We already passed these around. Do you know what that's called, by the way? It's called like quoits. I learned that because I have one at home now. C-O-I-T-S, quoits. I don't know why. I learned it from a children's book for my kids have. That will be used later today. This looks like something that could be, it's a bioscope. Looks like something that could be used, use the washer method to compute the volume of, so I'll probably pass that around. What other things we have? I don't know why we have this slinky in here, I'm not sure. Okay. I guess it's kind of, I don't know why there's in here. We don't have a ton of washer things. This one's not bad. I hesitate to pass it around because so it has a volume. This is like a thing that someone made for calculus actually. It has all these washers on it. But be very careful. It's very easy. Don't be the person who does it. Very easy for this to come out and then for it to spill all over. Okay. It wouldn't be the end of the world. But can you imagine? And why do we have this? Maybe this we'll use another day. This? Why do we have this? I don't know. We'll maybe look at that later. Where's that? There's something that I wanted in here that's missing, but okay. I don't know what happened to it.
What is it?
It's a little another washer. It's a very small, heavyweight thing. It's not. It's okay. All right. Did I give you enough time to buy enough time to help you digest all that? You feeling good about that? All right. So another approach. It says up on the slide here. Okay. So this time I'd like to use the same region, same 4 boundaries and everything. This time we're going to take a vertical slice. What? Still going around the y-axis, but a vertical slice. Well, what would happen with that vertical slice if you spin that vertical slice around the y-axis? What do you get?
Cylinder.
Yeah, or kind of you get a cylinder, but kind of a cylindrical shell, don't you? I'll show you my picture here. You kind of get this thin cylindrical shell that has a thickness of dx in this case, right? Like a very thin shell of a cylinder. And if you add up all those cylinders, you get the volume you need, right? So our task here will be to compute the volume of one of these small, infinitely thin shells, and then add them all up today. That's the game plan. So that's the idea here. We're gonna make an infinite number of cylindrical shells. Here we've pictured them with some thickness, but in reality there are an infinite number of them and they're all infinitely thin. And let's make a note too that as we begin this, notice that the axis of rotation is parallel, this time is parallel to the strip. In all the problems we did in the warm-up today and in last night's homework and everything, our strip was always perpendicular to the axis of rotation, wasn't it? So let's try to find just this one shell, for example. And in order to do this, I think that it's helpful. So the shells look something like this, right? Imagine that they have a thickness of dx. And what I'd like to do with you is kind of a picture unrolling this, one of these shells, and I'd like to think about how would you calculate the volume, this little dV, this little sliver of volume that we've cut in this strange fashion. Well, certainly we can think about the height, and that corresponds to the height of the rectangle here. The radius, how does that help us with the slab over here? Yeah, what is 2 pi r? Right? And then, of course, we've already said it, the width of the cylinder is dx, so that's also the width of the slab.
How can we do that? What if the circumference of the inside of the cylinder be smaller?
Yeah, so we're playing a little fast and loose here, but keep in mind that in the limit they're the same, right? Like when they're infinitely thin, they become the same. So there's definitely more we could say about that. And you're right to question the man, but look, just keep in mind that this is infinitely thin, so this does work. So of course the small sliver is 2 pi r h dx, yes? I just multiplied all the things you just said.
Yeah.
All right, so h is, let's go back to the picture. What's h? That's just given for this particular situation. That's just given by the distance from the x-axis up to this point on the curve, which is y. That's what it is, it's y. So what's y? X squared plus 1. So the height, at any given x value, if you wanted to compute this height, you would just use the function. What about we already have dx. What about r? We need that in terms of x as well. What is r? At any given x value, how would you say what r is? Don't think too hard. What is r? It's just x, right? Isn't x r? If we're at like 1.5, that is our distance away. Now, keep in mind, our axis of rotation right now is the y-axis. So x, by definition, is the thing that measures where we are with respect to the x-axis, with respect to the y-axis, right? So that's cool. So I think we can rewrite the volume of this slab now, not as 2 pi r h dx, but as 2 pi x, that's r. And instead of h, we can write x squared plus 1 for this particular problem. Right? Yeah.
Okay, I'm kind of like confused about what exactly we're calculating because don't we already know how to get the cylinder from what we have?
Say it again. The cylinder?
Like, this is to calculate like the area of the cylinder or the volume of the cylinder.
You mean you have before I said any of this, you knew how to calculate the volume of this cylindrical shell?
No. I'm saying, are we trying to calculate like just the shells, or
just one shell right now? Yeah, just one shell. Huh?
What like?
Oh yeah, because once we have one shell, just like we talked a lot about how to find the volume or the area of one washer. Once we find that, I hope you see that if we can get to the place where we understand how to negotiate this one shell, then we add them all up. And all of these shells, do you agree that all the shells like this, with radius between 0 and 2, that will be the whole volume. We're trying to picture that here, right? Each
Of the thing with the hole in it?
Yeah,
Oh.
right? Because each shell, if you can imagine, each shell will, if we add all those shells up, some of them are tall shells, some of them are small shells, right? All of those shells together will be the whole volume that we see. Hopefully we'll get the same answer. So, so this is called the shell method. And so here, I just copied from the last slide here. Yeah. The volume we said of this one cylindrical shell is 2 pi x squared plus 1 dx. And of course, integrating both sides gives us over all possible x values. What are the radii that we want? we want shells that have a radius as small as 0 and as big as 2, right? So add them all up is all an integral ever does for you, is just add up a bunch of things. And that gives us, well, do you remember what we got in the last one? 12 pi, right? Same answer. Now at this point, because this is still a little bit of a stretch, you may even still prefer breaking it up the way we did a second ago. And for this particular problem, you can do whichever you please. Questions, comments so far? I think that Jack's question is a good one. Can you visualize, I mean, maybe you're like comfortable with the shell, you're comfortable with all the things I've said, but you're like still struggling to see visually how all of those shells really do sum to the correct volume that we need, how those in aggregate really do form the volume that we claim they form. So that is I admit that that's a visual. Did I give you two? Yeah. No, you see on the paper we're about to do, we're going to do an example of both. Yeah, we can do shells with respect to both axes here. Okay? Again, emphasis is on the setup and the answer. Hopefully you can navigate your way through a problem like this, either with a calculator or without a calculator. So I'm going to walk through this first one with you, and I think for this one we might use a calculator just because it's a little messy. So help me out here again. We're rotating around the y-axis, so this is at the very least interesting. Do you see what you'll get here? You'll get, so we're taking this region, that is this parabola together with the x-axis, that region, and rotating around the y-axis. Can you picture that happening? The thing you'll get looks something like this, and I actually have this model with us here. Some of these need to be adjusted. Now you get the idea. And some of them are upside down. There we go. Okay, so I'll pass this around. But you can see these shells that together form the object there. So this is just a picture of that there. But can you picture how this is going to look and why decomposing it into a bunch of thin shells will in fact do the correct job of, if we sum them, giving us the correct volume. So what is the, what do we need here? 2 pi RH whatever, right? So we got the 2 pi, we got an integral. What are the limits of integration? What radii do we need? Keep in mind we're going around the y-axis, so what's the smallest radius of a shell? Huh? Oh, okay. We'll do both here. Let's do both. Let's do y-axis first, and then we'll also discuss how we would adjust it for y equals -1. Well, we can say both. What is the radius if we're going around the y-axis? It's just x. And what's the minimum radius we need? 2. And what's the maximum radius we need? 8, right? We're talking about these shells. We want to consider what's the shell with the smallest radius, what's the shell with the biggest radius. What else do we need? Okay, we also need the height of each shell. And for any x value between 2 and 8, the height of a shell will be given by the function. It's just y. It's just this function. So putting that all together gives us what we just said, right? 2 to 8. That's all the radiuses we're considering. 2 pi. What's our radius right now? X. What's the height? This whole nasty thing. And we'll just define it. Okay. It's not bad to do by hand actually. Get a phone nice, but. Now that's with, sorry, it was a little different on your sheet, I apologize. That's just around the y-axis. How would you modify it ever so slightly so that we're not going around the y-axis, but around what it says there, around the line y equals -1? say we're going around the line y equals -1 instead. What's the, yeah, x is what? I mean, that's the one thing we need to modify there, right? What is that? Huh? Yeah, it needs to be x plus 1 there. And are we still going from 2 to 8? This is the set of x values we're considering. I think that's okay, given that if we start at x equals 2, the radius here, x plus 1, gives us 3, doesn't it? Which is that inside radius. And if we go to 8, then that will be 9 here, which is what we want. So I think that's the only modification we have to do to make this work for your sheet. You'll have to run the numbers again. You will get a completely different volume. But the shape will look similar, right? It'll just be a little bigger of a hole. Okay. This method, the reason there's a bundt cake on the front is because that's what this looks like. Right, so there you go. So anytime you see a bundt cake or eat one, please think of the shell method. I'll skip the applet, but it lets you do the shell method to spin this around and see it green.
Do you have cake?
No, I'm sorry. That's a really huge disappointment, I'm sorry. It was not quite as easy. Maybe, I'm wondering if you could get mini bundt cakes somewhere or something. I don't know. Huh? Really? Alright, so Sophie's going to bring them on Monday, right? Everyone? See, I have to remind you guys that I'm a teacher, and feeding you 2 days in a row is a stretch. Yeah.
Okay. Is there a function that you could use to make a bundt cake?
Sure. I mean, if you don't like the one we gave you, you want one that's a little more accurate, you mean?
Yes.
Yeah, I might add like a sign next to it or something. Seriously, try it. Like add a little sign next to it. You want a little wave to it too, maybe. You can play around with this, Johnny. I think you'll come up with something great. Oh, I do have that x equals -1 there. Okay, so that's the only modification we talked about. On the back, let's just set this one up. And I'm sorry to run over here, but I think it's worth doing here. So how would you set this one up? Keep in mind that the strips this time, we're going around the x-axis, right? So it's the same problem. You still get the same picture. It's just what is everything in terms of this time?
Block.
Yeah, we get strips like this that we're going to spin around.
And you change the function in terms of
Well, look at it. Look at the function.
Oh, it's right here.
We're doing you a favor here. It's already in terms of y, isn't it?
yeah.
So that's actually us doing you a favor there. So that's a terrible picture, but you get the idea. So run the numbers. Why don't you set it up, and I'll compare answers in a minute. See if you can set up the integral. See if you can write the correct integral expression. The one thing I want to highlight today again, because after doing this, you're going to be like, I love the shell method. The thing that's going to mess with you, though, is when we throw these back into the mix. Would be okay? When we throw all these together into the mix. So I just want to emphasize today very strongly, especially as we go forward and practice some of these when they're all mixed together, that when we're doing the shell method, keep in mind that shell method is appropriate when your axis of rotation is parallel to the strips you have, right? Isn't that what we were doing today? Whether we're doing it with respect to y, like we just did, or with respect to x, the strips are parallel to the axis of rotation, right? And of course, always let geometry be your guide, right? So keep in mind that we also might move the axis of rotation, like we just discussed a little bit. It could be, like in this picture, that how do you get the height on this one? What's the height of this shell, like say right there? It's not this function. It's not really this function either. It's the difference between them, right? If you wanted to actually compute that difference, you might have to. We didn't go into that today, but I think there might be one on homework like that, so just keep that in mind. And I'll just put up as a review from the other day. What about the methods we've just been talking about, the washer method this past week? When is that appropriate? Well, that's appropriate when the strip you make, the way you're cutting the solid, is perpendicular to the axis of rotation. And again, that statement applies whether you're doing it with respect to x or y, right? If your strip you want to make is perpendicular to your axis of rotation, then you're talking about the washer method, okay? And these pictures tell it all. But again, I'll say the same comment. Let geometry always be your guide here. Draw the picture, draw the picture.
How do we decide which one to do? Can't we just do either?
Well, let's think. There's some that you can definitely do either on. Like this picture, for example. I mean, some of these, definitely. Like we opened with a problem that you could do both ways, didn't we? That's how we opened this lesson. Now, I want you to think hard about how you would do the problem that's right in front of you, using some other method besides the shell method. The bunt case here. Could you cut it horizontally? Notice that what would be the boundaries of your outer radius and your inner radius? It would actually be quite a bit of work to come up with that function. It'd be like the same function. It actually could be doable. I'd love to see you try. So you come back to me on Monday and see if you can figure it out. It's doable. It's not impossible. It's just not desirable. And I can think of worse functions where it really isn't possible, like at all. So there are cases where one method is simply not possible, but there are a lot of cases, like you're saying, where you could choose. Yeah. So that's why on the homework, did you catch the instruction again on the homework? There are two that I'd like you to redo using the shell method, like do both ways, right? Just to prove your point that you can do it both ways. Hopefully you get the same answer is the point.